As I mentioned before, there were a number of pretty good lab reports. As I graded more, I found more that were not quite so good. Main thing, guys, is you've got to read the guidelines. Okay? Got to read the guidelines. That's at least half the battle. The other battle is writing coherent sentences, and in terms of reading the guidelines, I thought the requirements for this lab were pretty clear to discuss what to discuss and how to prove your point. If those directions were not clear, please let me know. And really, the last 10% comes into just knowledge and, I mean, what you actually put forth and try to talk about. The main things is just following directions, including the general directions for any lab report and the specific for this particular lab report. To me, that's 90% of the battle. And from there, it can be very straightforward if you are familiar with the material we talked about and are able to make an argument using IR or melting point. Okay, we'll be moving into stereochemistry soon. I had a little mishap with email. Please have that one printed by Monday. Hopefully everybody has that now. Let's see where we're at. Okay, we're down here, the Wheel of Fortune here. We made our way around to last two reactions. These last two reactions are both ways to make alcohols. We saw a way to make an alcohol up top, and you have done that in lab. You hydrated norbornene to give an alcohol, norborneol. Two other ways to make alcohols. Of course, since we're under Roman numeral 2 here, or B on the other sheet, these do not involve carbocation intermediates. So what is the mechanism? What is the reagent? First off, this is mercury and water, followed by sodium borohydride. What is this? Then we'll look at BH3 followed by peroxide. Let's see here, guys. Good or no good? Okay. Very interesting reaction here. In step 1, what do we have after step 1 here? We have mercury acetate here and an OH here. This is what we had at the end of class. Just into step 1. I think so. Our OH is on the right carbon. No, that's not it. Here. This carbon, well, here it has a mercury. Here it has 3 H's. Here it has 2 H's and a mercury. In step 1, what have we done in the first step? What have we added to the alkene as a result of the first step? An oxygen and a mercury. This is called oxymercuration. We just did an oxymercuration reaction of the alkene. First word. Now, if we had used an alcohol, this would have been an OR group here. After we lost one H, we'd be left with the R group, and that would be alkoxymercuration. That's if you use an alcohol instead of water. The first step is followed by what step? Reduction. Sodium borohydride is a reducing agent. Structure of sodium borohydride. We have a boron with 4 H's. This boron is what charge? Negative, yes, and we have a sodium sitting with death. It's called borohydride. Borohydride. Sodium borohydride. Lithium borohydride. Potassium borohydride. I mean, it's any, just like potassium or sodium chloride. All right? Boron doesn't like being minus that much. I mean, it's not that electronegative. It hates being minus even more than carbon. Boron you can't please, because if it was just 3 H's, it would not have an octet. Of course, those bond angles are not correct. We would expect trigonal planar 120 bond angles there, but that's BH3, no octet on the boron. But it is neutral. Boron doesn't like being minus. It also doesn't like having no octet, so it's back and forth. But in this point, it's like, I don't want to be minus. What he can do, though, is he can say, hey, H, you and your electrons take a hike. And we can maybe show something like this. If these electrons just leave, what does that give? Well, it gives what I showed over there, right? Everybody see that? The H now has a lone pair. Yeah? And what do we call this? We actually saw it a week or two ago. What do we call that? No, it's not deuterium. It's just hydrogen. Hydride. Hydrogen anion. Hydride. All right? Now, this is not actually maybe formed here. These electrons may just move away and move directly where they're going to go. But basically, anytime you see sodium borohydride, it's a hydride source. It delivers H minus. Okay? Now again, I could do mechanism using this. I'm just sort of going to use H minus here. It's a little bit sort of in quotations here. But what do we need to do to get the final product? We need to replace the mercury with what? A hydrogen, yes, because there's 2 here, we need 3 there. We could perhaps show this with these electrons attacking the carbon and kicking the mercury off. That would give this, because now this carbon has 3 H's bonded to it, plus what? Mercury acetate. But regardless of what is on the mercury here, what do we added by this arrow? A lone pair. Yes. Final product plus that. What's the charge of the mercury here? If it's neutral here, it's going to be negative here. In terms of our organic product, we're done. We added this H. Anytime you add H's, that's typically known as a reduction in organic chemistry. If you remove H's, that's known as an oxidation. Sodium borohydride adds H's. Sodium borohydride is called a reducing agent. Here's our product. Oxymercuration followed by reduction with sodium borohydride. What's the fate of this? We can show this covalently. At this point, mercury doesn't like to be minus. It's a transition metal. We prefer to be positive or neutral. Well, acetate doesn't mind being minus. These electrons can leave. And what does that give? That gives mercury. We can show 1 lone pair just to keep it there consistent. There may be others. Plus what? Acetate. You should know the structure of acetate. 2 lone pairs here. The arrow gives us a 3rd lone pair. That's a minus. What's the charge of the mercury now? Neutral. We can sometimes show a 0 on top of that as the oxidation state is 0. That's mercury metal. It's atomic mercury metal. this reaction produces mercury metal. And because of that, it's not used that much in industry. Industry doesn't want to produce mercury metal. It's an old reaction. It's not used much anymore, but it's certainly still in organic textbooks and any other organic test. Very classical. Hopefully the error movement here is very rewarding to see how we get to such. And we don't just magically have to memorize, hey, it produces mercury metal. How does that happen? Well, hopefully we showed how it happened. And it can be, hopefully, you guys who are learning error movement say, yeah, I see that. Yeah, it makes sense. I see how mercury metal is formed here. So what did we do again in review? We took that, and now we have, if you look at formula, we've added H2O. We hydrated the alkene. Now, did we just react it with pure H2O? No, there's lots of reagents here, but formally, we hydrated the alkene by oxymercuration reduction. And we didn't get this rearranged here because there was no carbocation down here. We get the O on the place where the carbocation would be and no rearrangement. Where just aqueous acid would give a rearrangement because this reaction involves a carbocation. Okay, this is the standard product that we expect from where carbocation would be, called the Markovnikov product, standard. Below we'll see opposite from that. Okay, next reaction here. Questions about oxymercuration? Sodium borohydride will be seen, we introduce it here, you'll see it much more in organic 2. And you'll probably also, might even do a lab with it, but it's more common in organic 2 when we do carbonyl chemistry. Okay, another way to hydrate an alkene without rearrangement is hydrogenation oxidation. Another 2-step. We've added water to the alkene, but interestingly, the oxygen, which may have come from water if you think classical hydration, is out here. If you think carbocation, you're going to form carbocation there, right? And if you can envision the nucleophile water attacking here, you wouldn't get the oxygen over there. So that's an atypical product. It's called a non-Markovnikov product, or anti-Markovnikov product. Can you make such an alcohol from an alkene? Yes, not by those 2 methods up there, but by this method. BH3. BH3 again. We just had BH3 on the board. You may see it B2H6. That's the dimer of BH3. If you ever see B2H6, just mark it out and say BH3. It's the same thing. In terms of what's going on, it's just a dimer. Because BH3 is, you can't make it happy, and so the BH3 actually teams up to try to become happier. Makes a dimer. It's an interesting structure, although you guys probably shouldn't look at it because it has a hydrogen with 2 bonds. Don't tell anybody I said that. Okay, very unique structure. Okay, BH3, right? There's nothing here but BH3. That comes later. Well, what do we have? We've got BH3. What type of reactivity does that have? Does it have a positive charge? No. Does it have a partial positive? Does it look like it's polar? No. Why would electrons want to attack it? What is our reactivity? Why is it electrophilic? It doesn't have a full octet. It would like to have electrons to achieve a full octet. And something that would like to have electrons is called electrophilic. Something would like to have electrons. Well, here's some electrons, and these are going to be attracted there. What's the inherent attraction? Well, it goes back to why does boron want to be like neon? There's some driving force there that drives chemistry. I mean, it's got to be more than it just wants to be neon. It's got to be some physical physics or chemistry, right? Well, hopefully you discussed a little bit of that, Jim, why it wants to become neon, as opposed to that just being a rule. But that governs reactivity. These electrons are attacking. There's an empty p orbital here. These electrons are attacking. Where are we going to leave cation? Right or left? Left. So I'm going to pull away here and attack the boron. What does that give? It's going to give boom, 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 boom. Boron here, cation here, yeah. H, H, H. What's the charge of the boron? Now.
Negative.
Negative. We just saw a negative boron. That electron movement would give that. Well, some of you are already thinking, but hey, aren't we under B and there's no carbocation intermediate? Right? You're thinking that? Yeah, there is no carbocation intermediate. So why did I draw one? Well, I've been drawing them every time. Question is, what can we do here? What can happen here?
One of those H's can bond with an H, one of those boron H's bond.
Sodium borohydride, what was it a source of? H minus. Yes. This boron is no longer happy. It says, hey H, you and your electrons take a hike, and I want to go back to neutral. H and the two electrons take a hike, and this thing, it shoots darts. It shoots these hydride darts. These electrons here are moved over here. And that's a hydride shift. But it's not a 1-2 hydride shift like we saw before. It's a what? If the boron's 1, that's 2, that's 3. It's a 1-3 hydride shift. And what does that give? Boom, 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 boom. B, how many H's on the boron now? 2. I'm just going to show that condensed. Okay, there's no lone pair here. And I'll draw in this H here. Okay, this is not actually formed because the hydride shift takes place at the same exact time as this attacks. All right? Your boron with a hydride dart. Get your dart ready. Okay, I'm going to attack you, but as soon as I attack you, you got to back bomb. We'll make it work. Boom. That's it. That's the first intermediate. The first intermediate, well, we're making a ring. It's not a ring. It's not a ring because you're throwing a dart. You've got to throw your whole arm. You can't leave it connected. Okay? It's not staying connected. We're not making a ring. The whole thing is coming over. But it's concerted. All right? Hopefully you got that. It's one transition state leading directly to this. And that's it. That's in step 1. What have we done to the alkene? We got a hydrogen and a boron. We did a hydroboration of the alkene. But we got regiochemistry. We do not have the BH2 here and the new H there. How do you know that? You want to do it the other way and you want to switch that regiochemistry? How do we know that this is the way we go? Based on the what? Oh, well, you could. What about the mechanism? Right, because we would make carbocation here. And this boron, which we made minus by attacking it, throws an H at the carbocation. Okay? Why does Stephen show carbocations when they ain't really formed? Because I think they help you know how to do the chemistry. You base everything on where carbocation would form, even though it doesn't in this case. Or, unless you want to put carbocation out there. If so, we can have this attack this way and make boron here and leave that carbocation. Would you want to do that? Hope not. Now, a book is not going to show a carbocation because they're not going to say this is not actually formed. All right? The book is going to show a transition state. They're going to show partial bonds. They're going to talk about comparing the two transition states, and they're going to say that's the product. You can read that and try to understand that. If that works for you better than what I'm doing, then that's great. Again, it's a broken record. I'm showing you a carbocation. I'm doing it that way. Hydride shift. Here we go. We have regiochemistry. The boron is here, not there. It's regioselective hydrogenation of the alkene in step 1. What's the next step? Look at the reaction. How many H's here? 1. How many there now?
2.
Where did the extra one come from? The BH3. It's right there. It's the extra one. Okay. What do we need to do to get from the in step 1 product to the final product? What do we need to do to get here? We need to replace the boron with what? Yes. This is done with, you don't need to rewrite it, it's right there. It's done with hydrogen peroxide and some type of hydroxide, like KOH or NaOH. This replaces the boron with an OH. Importantly, whenever this takes place, there's no change in stereochemistry. Now, in my example, there is no stereochemistry, but when we have examples with stereochemistry, we need to know that whenever you do this step, there's no change in stereochemistry. That's very important. Right? And if we replace this with OH, right? On the right hand is a boron. Well, now it's an OH. And there it is. So, whenever you add oxygen, that's typically called an oxidation. So we have a hydrogenation followed by an oxidation. All right? Questions about this?
Yeah. So like, how do we? I mean, what do we just write now? Like, do we just, how do we know how do we like show that the OH is there?
Okay.
Like,
I was hoping for the question, but I was hoping for a word, though. Anybody got a question about this?
What is the mechanism?
Thank you.
that's what I meant.
Thank you. Good, because you're thinking mechanistically. You want to know mechanism. Good. Mechanism is magic. That's our mechanism. Okay, is that good enough for you? No. No? Good, I'm glad to hear it. You can look it up if you want, it's magic. I'm not going to go over it because it's too convoluted and doesn't match much of anything that we ever talked about. I don't think it's worth getting into. All right? We're just going to call it magic.
So we can put magic on the
I'm probably not going to ask you for that mechanism and just let you say magic. Okay? But I'm glad you want to know mechanism, because every reaction does have a mechanism of electrons doing something. Yes? Okay? Your book may or may not talk about it. It's a little bit unique and it doesn't fit in with introductory discussion, so I don't think it's worth saying, let's look at this. If you take an advanced course, you may get into some of it. If you do a Suzuki reaction, you know what Suzuki is? Used to be a motorcycle. Look it up. Suzuki reaction involves boron. It's a little bit there. Okay? All right, product here. Okay, show product in this first reaction. We've got a ring here. Again, you can show product with no stereochemistry if you want to first, and then go back and address stereochemistry. So, you got to have a little memorization and prompting, note card stuff. We got an alkene, because the rest is just non-reactive hydrocarbon, or alkane. Alkene, what does this do to an alkene? What is this? That's hydrogenation oxidation. What does that do to an alkene?
Add an alcohol on the carbon.
It effectively hydrates it and produces an alcohol. Is the OH going to be on, is it going to be a typical alcohol or atypical? Antimercarbonic alcohol. And actually that means the OH is going to be on the less substituted carbon. Now your book may tell you that the new H is going to be on the most substituted carbon. At this point you're going to be confused, and I don't blame you. Look at it and say, where are we going to make cation, and go from there. Okay? So, is the OH going to end up on top or bottom here? Bottom, because where's the cation going to be?
Top.
The cation does not really form, right? It would be on top. It means this attacks, right? BH3 attacks down, we leave cation, right? Let's do it mechanistically. And at some point, you do kind of need to get to where you can just think quickly and just have it, but it's all based on mechanism. Plus here, okay? So can you just draw the product, no stereochemistry yet? It's a crazy way to hydrate an alkene, and it gives the atypical antimercarbonic product. Everybody agree that's what we would get? Yes. Methyl there. So there's an OH here, and there's a new H here, and all that adds up to H2O. Okay? But look at that product. You have two groups on a ring. They can be cis or trans. Are those two groups going to be cis or trans? Cis or trans? Trans? Anybody else? Anybody with cis? Anybody not voting?
Dr. Stephen, the stereochemistry doesn't change, and you didn't give us initial stereochemistry.
No, stereochemistry doesn't change from the hydrogenation.
Oh, okay. Okay.
Whenever you replace the boron, whatever stereochemistry you had at the hydrogenation product, just replace the OH. Don't change any stereochemistry. We'll do it. All right, right? Let's see what we get there. BH3. That's minus. But this carbon's now tetrahedral. Once it attacks, it makes new bond. It can be forward or back. Let's call it forward. It can also be back. All right? What happens now? It throws an H dart over here, right? All right? Well, here's the kicker, here's the big thing here. This is forward. All right, this is now what, BH2? Still forward, it just threw a dart. Here's the kicker. Is the H forward or back? It's now here. It's forward. I made a bond to boron. We'll do cation, even though it's not there. And here's the cation. Now you're going to throw a dart here. Throw a dart. Okay? How's that dart going to be sticking out of the dartboard? From where it came from. Did you ever throw darts? If you throw a dart, when the dart hits the board, it's sticking which way? Towards you or away from you? Towards you, right? Unless you're throwing boomerangs, it's not going to be sticking away from you. The H came from the boron. It's forward, it throws an H. The H is going to be forward. Right? So the H is forward. By default, the methyl gets pushed back. There you go. Because the H comes from the boron. Now, that's in step one. What does the magic step do? You got an eraser? It does that. No change in stereochemistry. All right? There's your product. Now, the new H is drawn in. We can get rid of it so it looks a little cleaner. It's still there. And there's your product. The two groups on the ring are what? They're trans. Now, the OH and H are cis. But typically when you talk about cis or trans, you're talking about non-hydrogen groups. I mean, right? You're talking about the two substituents there. And the boron. The boron and the H are cis. That's why I haven't been referring to this each time, but that's why this is called, what type of addition of BH3? The boron and H are cis. It's also called syn, same side. Okay? All right? Of course, the last one gives what? This is going to be standard Markovnikov product, right? And that's going to give, well, you know what? Why don't you do that on your own? We need to move ahead. It really does you a disservice for me to just throw out the product and move on. You need to be able to put your own product in. All right? Otherwise, you'll just never think about it. Or you'll just look at it and say, yeah, that's a product. But unless you go through the process and struggle with the challenge of drawing it there, you're not going to learn as much. Okay. So we actually made it all around the Wheel of Fortune there. Hopefully these reactions are not as daunting now than maybe when you first looked at them. All right? Each one has unique reagents. But the core fundamental mechanism is very consistent. Okay, there's one other reaction to look at. And it's a reaction of an alkene with hydrogen, just H2. This is in the white handout. There's a couple of examples of these reactions here. We may have time to look at that, or basically those are the types of things that you need to look at on your own if you're interested. Reaction with hydrogen. Right here. Alkenes. Alkenes can react with hydrogen, H2, hydrogen gas. This is like bromination. There's no regiochemistry. It's one of the simplest reactions you'll ever see. We add an H to each carbon and you're done. If we add an H to each carbon, what functional group do we now have? It's no longer an alkene, but now it's an alkane. Because that product has a new H on each carbon. And now it's saturated. Unsaturated, saturated. So we're adding H's, so that's called a reduction, right? Reduction of alkenes with hydrogen. Mechanism. Hydrogen is not polar, and it's also not schizophrenic like bromine or chlorine, so it's not electrophilic by itself. But it turns out that in the presence of a precious metal catalyst, such as one of these, we can get a reaction. If you take bromine and react it with palladium, you'll make palladium bromide. You'll get a reaction. Turns out that hydrogen will also sort of somewhat react with metals. But if you just treat the hydrogen with the metal, you don't get an actual reaction or a new product, but you do get some interaction. And the interaction that occurs there allows this reaction to take place. This is not going to be a full mechanism. Mechanism is usually presented like this. Here's the metal surface. The hydrogen sort of absorbs to the metal. There's an interaction there. Okay, it's a little bit nebulous and not well defined. But the interaction leads to reactivity. The pi bond approaches all this, and the H's become like darts, and they shoot into the pi bond. There's your scientific mechanism, okay? Two H's shooting in there. Okay? This is sort of showing it. And the two H's are now added, one to each carbon. Importantly, because the H's came from the metal surface, the two H's are shot in from the same side. So it's a syn addition. Cis-syn addition. All right? If you want more details about how this might happen, well, start with your book and then move on from there. It's not an ionic mechanism. There's no ions anywhere. There's only one transition state. It's just H's in. You got to have the metal, precious metal like palladium or platinum or nickel. Things we can say about this. Both of these alkenes give the same product upon hydrogenation. You should see that. I mean, if you add an H to each of here, you get that. Or here, you get that. Questions we could ask here. Which route would be more exothermic? This route or the bottom route? Both give the same product. Which would be more exothermic? Reaction coordinate diagrams. Okay. Very important to be able to draw out a reaction coordinate diagram and use that to help you answer things. Very much just like during test 1, I tried to get you to graph hybridization. Very fundamental, and get your answer. Reaction coordinate diagram, get your answer. You need to be able to do that. We'll answer that next time. Over here, you take this alkene, we're doing a hydrogenation. We're going to add an H to each carbon. This product's got two substituents, ethyl and methyl. They will be cis. Because it's a cis addition of hydrogen. By the way, deuterium, D2 is also commonly used, at least in class and quiz and test. By the way, we'll have a quiz on Monday on our alkene reactions. Okay? Why are these cis? Well, how are the H's here? The H's are both back. The H's are cis because they came in from the same side. What other product are we going to get here? You actually get another product here.
They just came in from the other side, right?
Yes, this is where the metal was in the back and it shot the H's in from the back. But you could also have the metal in the front and it shoots the H's in from the front, and that would give but it's still cis. Cis only. Are these the same or different? All right. You want to draw the H's in here? They're both forward. Same or different? No, these are actually different. Okay. These are enantiomers. A lot of times this may be shown this plus enantiomer. So if you ever see that, well, that's the enantiomer of that. Remember, on enantiomers, everything's reversed. So you've got to be careful. Just because you reverse everything doesn't mean it's the enantiomer. That's our next topic. Stereochemistry. Well, we got a little bit more here, and so we're probably not going to get to stereochemistry today. Please be looking ahead. You have the one to print and the pink one. Really, we go ahead and answer this. Why don't you look at this? I don't think we have enough time to get into it. Why don't you look at that and try to answer those questions? We'll answer them quickly on Monday. Okay. Let's set the stage a little bit for stereochemistry. There's a pink handout. The paragraph at the top is some of my description of the big story there. Okay. Chirality. And this is where we, like right there, plus an enantiomer. Okay. Last day or so, I tried to show these two compounds. We've got a carbon with 4 different groups attached. That's what I'm trying to illustrate here. Carbon with the same 4 different groups attached. Okay? As they're attached here, these are mirror images. If that looks in the mirror, it'll see this. Okay? They are mirror images. But everything's got a mirror image. If that looks in the mirror, it'll see that looking back at it. Okay? Oh, wait, except for a vampire. I don't think a vampire's got a mirror image. Okay? Are these the same or different? Well, if they're the same, you should be able to stack them. Or maybe not stack them, because you can't stack these because of the way they are. But what you should be able to do is, if these were, is it a hologram or something? Like just something. This should be able to move and sit directly on that one. Okay? And that's called superimposing something. Your coffee cup saucers in your cupboard are all identical. That's why you're able to just stack them in there. You got 6 in there. Okay? Are these superimposable? If we took this and moved it and set it right on top, is it the same?
No.
That's quick. No, the red and blue don't line up. Well, that's okay. We can make them line up. Yes. Now the red and blue line up. Huh. Uh-oh, now the green and gray don't. They never will. They're not the same. Mirror images that are not the same are called enantiomers. Okay? Your hands are enantiomers. All right? They have the same connectivity, a carbon bonding to the same 4 groups. And it could be a bigger molecule, and we'll do more and more, okay? That looks in the mirror, we'll see this. Okay? Are these superimposable? Can you stack them? No, I've got a thumb on one side but not the other. Are these the same or different? If I had a right-handed glove, will both fit into it just the same? No, only this one will fit into the right-handed glove. They must be different. They are. Same connectivity. They're mirror images that are different. Now, if I had this and then I had a hand where the pinky was connected over here, those would not be mirror images. This has the same connectivity, just like those molecules do. Okay, please be getting into this. You have your hand down, and you got one you need to print. We'll be looking at that on Monday. See some of you in lab this afternoon upstairs, right?
Anthropology.